Welcome to my channel MathAlcoholic. So in this video I'll be starting from question number 11 onwards. In the previous video I did elaborately discuss question number 10, although such an elaboration was not required for a student in class 12, but still. So in the question number 11 we need to find a matrix X so that X multiplied this matrix is equal to this matrix. Now what we need to observe is that this matrix 1 2 3 4 5 6 is of the order 2 by 3. And the resultant matrix is also of the order 2 by 3. So this is only possible. First of all, matrix multiplication is only possible if the number of columns of the first matrix is equal to the number of rows of the second matrix. Alright? And the order comes out to be m by z, as you know it. Now conversely checking, this is only possible, this matrix multiplication is only possible when the number of columns in X is 2. Alright, and so this 2 and 2 you just vanish it in your mind, and the number of rows you will get from this. So the number of rows should also be equal to 2. So 2 by 2 matrix multiplied by 2 by 3 matrix would yield you a 2 by 3 matrix, and there is no other possibility. So since X is a 2 by 2 matrix, let X is equal to A, B, C, D, as we don't know anything about it, right? So let us check it out right now. So it is A, B, C, D multiplied by 1, 2, 3, 4, 5, 6, which is equal to -7, -8, -9, 2, 4, 6. Alright, so this is going to give you A plus 4B, 2A plus 5B, 3A plus 6B. Alright, and here it is C plus 4D, 2C plus 5D, and 3C plus 6D. Here it is -7, -8, -9, 2, 4, 6. Now for these two matrices to be equal, all these equations should be satisfied. So A plus 4B must be equal to -7, 2A plus 5B must be equal to -8, 3A plus 6B must be equal to -9, and here similarly C plus 4D must be equal to 2, 2C plus 5D must be equal to 4, and 3C plus 6D must be equal to 6. See, we have two variables but three equations, so one equation is completely unnecessary. That means that the value of A and B that we will be finding from any equation must also satisfy the third equation. Alright, here in both the cases. So here let's find out AB at first, then we will be finding C and A at first. There are many techniques, you can take any of the two. See, I am taking this two because of my personal convenience. Why? See, I can easily reduce it into, by dividing 3 on both sides, we get A plus 2B is equal to -3. Alright, so taking these two equations and subtracting this equation from this equation, or this equation from this equation, you may do anything. So I do A plus 4B minus A plus 2B, that is equal to -3, -7 minus of -3. So I get here that is 2B is equal to -7 plus 3. So 2B is equal to -4 and B is equal to -2. Alright, now if B is equal to -2, A is equal to, clearly it is -1. Am I right? No, I guess I am wrong. A is equal to +1. Now you can put it in the second equation to satisfy it. Do you see it satisfying it? Yes, it does satisfy the second equation too. Similarly here, in case we divide it by 3 on both sides, so we get C plus 2D, that is equal to 2. Subtracting this, we get D is equal to 0. And if D is equal to 0, C is clearly equal to 2, and this satisfies once again the unsolved equation. That means A, B, C and D are completely perfect. Hence the matrix X is equal to A, B, C and D. Alright, this is the matrix. I hope that's an easy catch. Now coming to the next question. Coming to question number 12, it is quite an easy one. We need to prove by induction, and we did many problems before. So we'll start by the given data. So sorry, given that A and B are square matrices, obviously it should have to be of the same order such that AB is equal to BA. Alright, now we need to prove that P of n, let us assume it to be a statement which we need to prove, b to the power na for all n that belongs to natural numbers, set of natural numbers. So for n is equal to 1, we have P of 1, that is AB1 is equal to B1A, that implies AB is equal to BA, and that is given. So hence n equal to 1 satisfies Pn. Now let the result be true for n is equal to k. Therefore P of k is equal to P of k, it is such that AB to the power k is equal to B to the power k A. Let this be question number 1. Now if we can show that P of k plus 1 also belongs to the same category, then we can prove this. So this is AB raised to the power k plus 1, which is equal to AB raised to the power k multiplied by B, which is once again B raised to the power ka multiplied by B, and this is from assuming equation 1. Now this is equal to B raised to the power k AB, which is again equal to B raised to the power k BA, given AB is equal to BA, and again by associative law we have B raised to the power k B multiplied by A, which is equal to B raised to the power k plus 1 A. Alright, so we can say the result is true for n is equal to k plus 1. Then by principle of mathematical induction, A B raised to the power n is equal to B raised to the power n A for all n belongs to capital N. Alright, now let us assume it to be question number 2, as we will need it later. Now assuming that, we have to prove further that A B raised to the power n is equal to A raised to the power n B raised to the power n for this condition. Alright, now so we have assumed this to be condition 2. Once again we prove that AB raised to the power n is equal to A raised to the power n B raised to the power n for all n belongs to the set of natural numbers. For n is equal to 1, that's a plane in late night, then at late night, please don't mind the plane, goes on ahead, I can't do anything genuinely. So for n is equal to 1, we get here AB raised to the power 1, that is equal to A raised to the power 1 B raised to the power 1, and that is equal to AB. So we can see that result is true for n is equal to 1. Now let this result be true for n is equal to k. Therefore AB raised to the power k is equal to A raised to the power k B raised to the power k. That is, let us assume it to be question number 3. Now we have to prove this result to be true for n is equal to k plus 1. So AB raised to the power k plus 1, that is equal to AB raised to the power k multiplied by AB, that is equal to A raised to the power k B raised to the power k multiplied by AB, which is by 3. You can clearly see here I have assumed this equation 3, and putting that we get this. Now this is equal to A raised to the power k B raised to the power k A into B. Alright, this is by the associative property. Now similarly we can write it to be A raised to the power k A B raised to the power k B. Okay, this is from 2. We had assumed that equation, which got out to be true. We proved it. Once again by associative property, we take A raised to the power ka and b raised to the power kb, that is equal to a raised to the power k plus 1 b raised to the power k plus 1. Once again we can see that ab raised to the power k plus 1 is a raised to the power k plus 1 b raised to the power k plus 1, hence it holds true. So therefore the result is true for n is equal to k plus 1. Hence by mathematical induction a b raised to the power n is equal to a raised to the power n b raised to the power n for n belongs to n, right? So I think that this was a lengthy video and it deserved it. Now I'll be discussing the last video of this exercise, where I will be discussing only the objective questions in the next video. Keep watching. Thank you very much for watching this video.